In the last few lectures, we've been reviewing one-way ANOVA, analysis of variance. In this lecture video, we're going to do another example to help solidify the procedure in our minds. Here's an outline of what we'll be looking at in this video. We'll first provide a description of the experiment and take a look at the data. We'll then perform the ANOVA by hand using the calculations that we reviewed in a previous lecture video. We'll then construct two confidence interval estimates of the model error variance. One is based on the chi-square distribution, and the other is based on the normal distribution. We're also going to perform the ANOVA using SAS. We'll use both PROC GLM and PROC Mixed. In doing this, we're going to obtain a confidence interval estimate of the model error variance based on the chi-square distribution, and we'll do this by first programming the calculation in a data step, and we'll also see how to get it directly from SAS PROC Mixed. And then finally, we'll determine whether the confidence intervals for the model error variance can be relied upon by checking the plausibility of the model assumptions and also evaluating how well the chi-square sampling distribution of the point estimator of the model error variance can be approximated by a normal distribution. So let's jump in. We're going to call this example 3.2, and this is a comparison of river influent nitrogen concentrations. Here's a description of the experiment. A researcher was interested in comparing the nitrogen concentrations of 6 particular influents flowing into the Mississippi River. Water samples were obtained from a number of locations at each influent. The size of the influence varies, and the number of locations at each influent from which water samples were obtained was approximately proportional to the size of the influent. Because of this, the sample sizes vary from one influent to another. A total of 37 water samples were obtained. Let's take a look at the raw data and the basic summary statistics. Here we have a tabular representation of the data set. The columns in the table correspond to the 6 influents, or the 6 samples that we have. The body of the table contains the raw data. And at the bottom of the table, we have 4 summary rows. These are summaries of the 6 influents or 6 samples in the data set. And so we have a row for the various sample sizes. We have a row for the sums of the observations within each sample. We have a row for the mean response, the mean nitrogen concentration for each of the 6 samples. And then finally, in the last row, we have the sums of squared observations for each of the 6 samples. In the far right column, we have overall summary statistics for the entire data set. And so we have the overall or total sample size, which is 37. We have the sum of all the observations in the data set, which is 776. We have the sample mean, the overall sample mean for the data set, which is obtained by dividing the sum, 776, by the sample size, 37. And that gives us an overall mean of 20.9730. And finally, we have the overall or total sum of squares for all the observations in the data set, and that's equal to 19,520. Now we're going to be using these values in calculating the various sums of squares for the analysis of variance. Before we do that, let's look at the ANOVA table and compute the degrees of freedom for that table. So we have 6 treatments or 6 influents, and so we have 6 minus 1 or 5 degrees of freedom for treatments. There are 37 observations in the data set, and so there are 37 minus 1, or 36, total degrees of freedom available to us. And then finally, to get the degrees of freedom associated with error, we subtract the degrees of freedom for treatments from the total degrees of freedom. And so this is 36 minus 5, or 31. Now let's calculate the sums of squares for the analysis of variance. Now you'll recall that in order to calculate the corrected sums of squares for the analysis of variance, we typically use a computational or shortcut formula in which we calculate the uncorrected sum of squares and then we subtract from that a correction factor. The correction factor is equal to the square of the sum of all the observations in the data set divided by the total sample size. And so for this data set, for this analysis of variance, the correction factor or correction term is equal to the square of 776 divided by 37. And so that's equal to 16,275 and then some change. The total corrected sum of squares is obtained by calculating the total uncorrected sum of squares and then subtracting from that the correction factor. From the summaries in the data table, we saw that the total uncorrected sum of squares was 19,520. We subtract from that the correction term, and so we get the total corrected sum of squares equal to 3,244.97297. The treatment sum of squares turns out to be 1,925.193605. And then once we have the total corrected sum of squares and the treatment sum of squares, we get the sum of squares for error by subtraction. And so this turns out to be 1,319.779368. And so now we can fill in the sum of squares column of the ANOVA table. And so the total sum of squares is 3244.97297. The treatment sum of squares is 1925.19361. And the sum of squares for error is equal to 1319.77937. Now we can calculate the mean squares for the analysis of variance. You'll recall that in general, the mean square for a particular source of variation in the ANOVA is obtained by dividing the sum of squares for that source of variation by its degrees of freedom. And so the mean square for treatment is equal to SST, the sum of squares for treatment, dividing that by t minus 1. So 1925.193,60789 divided by 5. And that turns out to be 385.03872159. The mean square for error is equal to the sum of squares for error divided by its degrees of freedom, which is n minus t. And so 1319.779366508 divided by 31. And so the mean square for error is equal to 42.5735279058. And so now we can fill in the mean squares column of our ANOVA table. And now that we have the mean squares, we can calculate the F statistic. For this one-way ANOVA, the F statistic is equal to the ratio of the mean square for treatments to the mean square error. And this turns out to be 9.04408774. Let me just point out that the ANOVA table is not only a way to help display the work that we've done, but it also helps facilitate the calculations for the mean squares and the F statistic. Once we have the degrees of freedom filled in, and we've calculated the sums of squares, we can calculate the mean squares by dividing the sum of squares in a particular row by the degrees of freedom in that row. And so it's very easy to remember how to calculate the mean squares for this analysis. And once we have the two mean squares, then we get the F statistic by taking the ratio. And so it not only presents a summary of the calculations, but it also helps us to remember how to do some of these calculations. Here we have the data set and the calculations for the ANOVA done in the context of a spreadsheet. At the top, we've got the data set, and right below that, we've got summary statistics for each of the samples in the data set. On the far right-hand side, we've got summary statistics for the overall or combined data set. And below that, we've got calculations for the correction factor, as well as the three sums of squares for the ANOVA. Once we have all that, we can construct the ANOVA table, and the entries in the table are programmed to pull the relevant information from the calculated cells above. And so you can see here, for example, that the F statistic is 9.044-08774, which is the same as we got calculating it by hand. In addition to that, we also have the ability in the context of a spreadsheet to calculate the p-value of the test. In this case, it is 0.000022. Now, the p-value for this test is defined to be the probability of observing an F statistic greater than or equal to that which we have observed for the data set, which in this case is 9.044, for an F distribution with 5 numerator degrees of freedom and 31 denominator degrees of freedom. Now, the F statistic is equal to the ratio of the mean square for treatments to the mean square error. If the nitrogen concentration means are the same at all 6 influence, then the MST, the mean square for treatments, and the mean squared error are estimating the same quantity, and therefore their ratio will tend to be close to 1. If the nitrogen concentration means differ across the 6 influence, then the MST is estimating a quantity that is strictly larger than the MSE, and so their ratio will tend to be larger than 1. In this case, the MST is 9 times larger than the MSE. And so this is evidence that the nitrogen concentration means differ across the 6 influence. The question is, how strong is this evidence? The hypotheses being tested by the ANOVA are as follows. The null hypothesis is that mu1, mu2, and so forth up to mu6 are all equal. That is, that no differences exist among the 6 population means. The alternative is that the means are not all equal, that is, that differences do exist among the 6 population means. Now again, mu sub I is the mean nitrogen concentration for influent I, where I goes from 1 to 6. The test statistic, as we've seen, is equal to 9.044, rounded to 3 decimal places. We're going to be performing this test at the 0.05 level of significance, and so the critical point for the test is the upper 5th percentage point of the F distribution with 5 numerator degrees of freedom and 31 denominator degrees of freedom. And that is equal to 2.523. The p-value for the test is equal to 0.00002224. Now we see that the test statistic, 9.044, is greater than the critical point, 2.523. The p-value is certainly less than 0.05. And so we conclude that there is sufficient evidence at the 0.05 level of significance to reject the null hypothesis and conclude that the mean nitrogen concentrations differ across the 6 influence. Now we're going to construct confidence interval estimates of the model error variance. The first interval is going to be based on the chi-square distribution, which, if the model assumptions are true, is the true sampling distribution of the estimator of the error variance, sigma hat squared. A 95% confidence interval estimate of sigma squared, the variance of the model error term, based on the chi-square distribution, is given by the following construction. And so we see here that both the lower and upper endpoints have the same numerator in these formulas. The degrees of freedom for error times the point estimator of sigma squared. Where they differ is in the denominators of those formulas. The denominator for the left endpoint is the upper alpha over 2 percentage point of the chi-square distribution with degrees of freedom equal to the error degrees of freedom. And for the upper endpoint, the denominator is the upper 1 minus alpha over 2 percentage point of the chi-square distribution with degrees of freedom equal to the number of error degrees of freedom in the ANOVA. Since we're constructing a 95% confidence interval estimate, alpha is equal to 0.05, and so alpha over 2 is equal to 0.025, and 1 minus alpha over 2 is 0.975. And so the denominator for the left endpoint is the upper 2.5 percentage point of the chi-square distribution with 31 degrees of freedom. That's equal to 48.232, rounded to 3 decimal places. And the denominator for the upper endpoint is equal to the upper 97.5 percentage point of the chi-square distribution with 31 degrees of freedom. And that's equal to 17.539. And so the 95% confidence interval estimate of sigma squared based on the chi-square distribution is given by the interval that ranges from 27.36 up to 75.25. Now note the asymmetry of this confidence interval about the point estimate, sigma hat squared equal to 42.5735. The length of the portion of the interval above the point estimate is equal to 32.68, while the length of the portion of the interval below the point estimate is 15.21. We see that the portion of the interval above the point estimate is 2.15 times longer than the portion of the interval below the point estimate. Now, as we discussed in the previous lecture videos, this is actually a desirable feature because the sampling distribution of sigma hat squared is right skewed. And so this method of constructing a confidence interval for sigma squared takes into account that skewness. Now let's compute a confidence interval estimate of sigma squared based on the normal distribution. An approximate 95% confidence interval estimate of the variance of the model error terms, sigma squared, based on the normal distribution, is given by the following construction. The lower endpoint is given by the point estimator, sigma hat squared, times the quantity, 1 minus z sub 0.025, 1.96, times the square root of 2 over the error degrees of freedom, which are 31, and that gives a lower endpoint of 21.38. The upper endpoint of the interval is given by sigma hat squared times the quantity, 1 plus 1.96 times the square root of 2 over 31, which gives 63.77. Note that this confidence interval is, by construction, symmetric about the point estimate, sigma hat squared. The lengths of the portions of the interval above and below the point estimate equal to 21.19. Now again, I just want to emphasize that what we are constructing here is a confidence interval estimator that has a confidence level of approximately 95%. Now we're going to perform the analysis in SAS. The first step is to create a data set containing our data, and we do that using the data step. And so here is the data step to create the SAS data set. To do the analysis of variance, we're first going to use SAS PROC GLM. Here's the SAS code to perform the ANOVA using PROC GLM. I invoke the procedure using the PROC GLM statement, and I tell PROC GLM the data set to use by specifying data equal nitrogen. The class statement identifies the classification variable to SAS, the classification variable being the variable that identifies the different samples. In this case, that variable is influent. And then I specify the model for the analysis, and since this is a one-way analysis of variance, the model is concentration, the response variable, equal to influent, the one classification variable. I'm going to save the residuals from the model to an output data set, and then I've got an LS mean statement and a mean statement. We'll talk about that later. And so here is the analysis of variance performed by PROC GLM. And you can see here that we have 5 model or 5 treatment degrees of freedom. We have 36 total degrees of freedom, and we have 31 error degrees of freedom. If you compare the various sums of squares, the mean squares, and the F statistic to those we calculated by hand, you'll see that these values agree with those values. Next, we're going to construct a 95% confidence interval estimate of the error variance, and we're going to do this based on the chi-square distribution. Here's the SAS code to calculate the confidence interval estimate of the error variance, and as you can see, I've programmed this in a data statement. The confidence interval that we obtain ranges from 27.3632 up to 75.2494, and that's the same that we got when we did this by hand. Next, we're going to perform the analysis of variance using PROC Mixed. Here's the SAS code to perform the analysis of variance using PROC Mixed. We invoke the procedure with the PROC Mixed statement. We specify the data set to use, and then I've also got a few options here: method equal type 3, cove test, and the CL for confidence limits options, and we'll see the results of those in a second. We specify the classification variable to PROC Mixed, and we specify the model, which in this case, because this is just a fixed effect model, it's the same as it was in PROC GLM. So model concentration equal to influent. Here are the results of this analysis. The method equal type 3 option instructs PROC Mixed to perform a type 3 analysis of variance. This is the same method of analysis that PROC GLM used, and so we will get consistent results. We have a column for the degrees of freedom, and as you can see here, we have 5 treatment or 5 influent degrees of freedom, and we have 31 error or residual degrees of freedom. We have a column for the sums of squares, and these are equal to the sums of squares that we obtained previously. We have a column for the mean squares. These are also equal to what was obtained previously. This also provides a column labeled error degrees of freedom. And this is giving us the number of error degrees of freedom for testing the significance of a particular effect. Now, because we have a simple one-way fixed effects model, the error degrees of freedom in that first row are the same as the error degrees of freedom in the first column. The F value for this test is 9.04, which is the same as we obtained before, and the P value is less than 0.0001. Now, what is being tested by this F value? What is being tested by the P value? Well, to answer that question, we need to look at the expected mean square column. The expected mean square for treatments, influent, as we can see here, is equal to the sum of 2 components, the variance of the error term and a quadratic form involving influent. This quadratic form is equal to 0 if and only if the nitrogen concentration means are the same at all 6 influents. This implies that the expected mean square for treatments will be equal to the expected mean square for error if and only if the nitrogen concentration means are the same at all 6 influents. Therefore, the hypotheses being tested are as follows. The null hypothesis is that mu1, mu2, mu3, and so forth up to mu sub 6 are all equal, against the alternative that at least one of the means is different than the rest. Next, let's look at the output produced by the Cove test and CL options. The Cove test option tells PROC Mixed to test the significance of all of the random components in the model. In this model, we only have one random component, the error term. And so in this case, the Cove test option is testing the null hypothesis that the variance of the error terms, sigma squared, is equal to 0 against the alternative hypothesis that sigma squared is greater than 0. As we can see, the p-value of this test is less than 0.0001. And so based on that, we would conclude that the error variance is greater than 0. This conclusion is really not that surprising, and this test is really not of interest in this particular situation. This kind of test becomes much more important and interesting when we have more than one random component in the model. The CL option tells PROC Mixed to construct a confidence interval for the variance of every random effect in the model. In this model, we only have one random effect, the error term, and so PROC Mixed is going to construct a confidence interval for sigma squared. Now this particular confidence interval is based on the chi-square distribution and is equal to the confidence interval that we got when we constructed it by hand. Now let's compare and evaluate the two confidence intervals that we constructed for sigma squared. The 95% confidence interval estimate of sigma squared based on the chi-square distribution ranged from 27.36 up to 75.25. The width of this interval is 47.89 units. The approximate 95% confidence interval estimate of sigma squared based on the normal distribution ranged from 21.38 up to 63.77, and the width of this interval is 42.39. The interval based on the normal distribution is more precise. It's about 12% narrower than the interval based on the chi-square distribution. We can see here that the interval based on the normal distribution reaches farther to the left and not as far to the right as the interval based on the chi-square distribution. This is because the interval based on the normal distribution does not take into account the skewness associated with the sampling distribution of sigma hat squared. And so are either of these intervals trustworthy? Can either be relied upon? Each has a nominal confidence level of 95%. But can we have confidence that the true confidence level of either interval is, in fact, 95%, or at least close to it? Here's some questions to look into to answer this. Are any of the model assumptions violated? How well is the chi-square distribution with 31 degrees of freedom approximated by a normal distribution? In particular, how skewed is this chi-square distribution? And how much kurtosis does this chi-square distribution possess? Let's first check for violations of model assumptions. We'll first look at the normality of the error terms. And so here we have PROC univariate code to analyze the residuals from the model. The normal test option is going to perform a formal test of the null hypothesis that the residuals from the model come from a normal distribution. The histogram statement will produce a histogram of the variables in the var statement in this case, the model residuals. The normal option to the histogram statement will superimpose a normal distribution that has the same mean and variance as residuals over the histogram for comparison purposes. And finally, the PP plot statement will produce a probability plot of the residuals versus corresponding values from the normal distribution with the same mean and variance as the residuals. The QQ plot provides a similar kind of plot, a quantile-quantile plot, but we're going to focus on the PP plot. Now here is a histogram of the residuals with a normal distribution superimposed on top of the histogram. And so how would you characterize the shape of this distribution? It's not perfectly symmetric, but would you characterize it as skewed to the left or skewed to the right? Numerically, we can see here that the skewness coefficient is negative, so there is some slight left skewness or negative skewness in the data. Here we have the PP plot for the model residuals. This is essentially a scatter plot of the empirical CDF of the residuals versus the corresponding values from the CDF of the approximating normal distribution. Now, if the model error terms are indeed normally distributed, then the points on the graph should fall closely to the line. As we can see, the points do very closely follow the line, and so in this graph there really is no evidence against the normality assumption. This table provides a formal test of the normality of the residuals. In fact, it provides 4 different tests. And so the question is it reasonable to assume that the model error terms are normally distributed? As we can see, the p-values for all 4 tests are larger than any significance level that we would really ever use in practice. And so there is really no evidence in this formal test that the model error terms are not normally distributed. Therefore, the assumption that the model error terms are normally distributed is reasonable at any significance level that we would ever use in practice. Next, let's look at the constant variance assumption of the error terms. And so here in the GLM procedure, we issued the means statement, and as an option to the means statement, we had the HOV test option. The HOV test option of the means statement in PROC GLM performs a test of the homogeneity of variance assumption. And so this table provides the results of that test. This is testing the following hypotheses. The null hypothesis is that the error variance is the same under all treatments. The alternative hypothesis is that the error variance differs from one treatment to another. Since the p-value, which is 0.2994, is greater than any significance level that we would ever really use in practice, the constant variance assumption is indeed reasonable. Next, let's look at what the chi-square distribution with 31 degrees of freedom looks like. Here we have a plot of the PDFs of the chi-square distribution with 31 degrees of freedom and the normal distribution that has the same mean and variance as that chi-square distribution. The blue curve is the chi-square PDF, and the red dotted curve is the normal PDF. And so you can see here that there is some skewness to the blue curve, however, there's not much. The normal PDF, the red dotted curve, is quite close to the chi-square PDF. The skewness of this chi-square distribution numerically is equal to 0.51, which is really not that much greater than 0. 0 being the skewness coefficient for the normal distribution, or in this case, that red dotted curve. In addition, the kurtosis of this chi-square distribution is 3.39, which is only 13% larger than the kurtosis of a normal distribution. Recall that the kurtosis of every normal distribution is 3. And so you can see here that the PDFs of these two distributions are quite similar. Now, when comparing two distributions, a better comparison than comparing the PDFs is to compare their CDFs, their cumulative distribution functions. This graph shows the CDFs of the chi-square distribution with 31 degrees of freedom, which is the blue curve, and the approximating normal distribution, which is the red dotted curve. Note how close the normal CDF is to the chi-square CDF. We can see here that in this situation, the normal distribution actually provides a good approximation to the chi-square distribution. So which of the confidence intervals for the error variance can we trust? Regarding the confidence interval based on the chi-square distribution, recall that these confidence limits are accurate and the confidence level is exact, as long as the assumptions about the model error terms are true. If the assumptions are not true, then the confidence limits and confidence levels will be approximate at best. The more closely the assumptions are to being met, the more accurate the confidence limits and confidence levels will be. Now, we found that there is no evidence that the normality assumption is not true. In addition, there is no evidence that the constant variance assumption has been violated. And so therefore, we can conclude that the confidence limits are accurate and that the true confidence level is very close to and perhaps equal to the nominal level of 95%. Next, regarding the confidence interval based on the normal distribution, recall that in addition to the model assumptions needing to be met, the accuracy of the endpoints and the confidence level of this confidence interval depends on how well the true sampling distribution of sigma hat squared can be approximated by a normal distribution. The sampling distribution of sigma hat squared, if the model assumptions are true, is the chi-square distribution with 31 degrees of freedom. And we have found that this distribution is closely approximated by the normal distribution that has the same mean and the same variance as that chi-square distribution with 31 degrees of freedom. And because of this, we can conclude that the true confidence level for the interval based on the normal distribution can be expected to be close to the nominal level of 95%. So which confidence interval should we use? Based on our analysis, the confidence interval based on the chi-square distribution should have a true confidence level of 95%. The confidence interval based on the normal distribution may have a true confidence level that is close to 95%. Since the chi-square distribution is the actual sampling distribution of the point estimator of sigma squared if the model assumptions are true, while the normal distribution is an approximation to that distribution, an interval based on the chi-square distribution would still be preferable, at least if it's available. We would therefore choose to use the interval based on the chi-square distribution. So let's summarize what we've done. We provided a description of the experiment. We then performed the ANOVA by hand using the procedure described in a previous lecture video. We constructed two confidence interval estimates of the model error variance, one based on the chi-square distribution and the other based on the normal distribution. We also performed the ANOVA using SAS, using PROC GLM and also PROC Mixed. We obtained a confidence interval estimate of the model error variance based on the chi-square distribution by programming the calculation in a data step, and also we obtained it directly from SAS PROC Mixed. We concluded that the model assumptions appear to be met. And finally, since the model assumptions do appear to be met, the interval based on the actual sampling distribution of the point estimator, the chi-square distribution, would be the preferred interval to use. If, for some reason, the interval based on that chi-square distribution were not available, then in this particular case, the interval based on the normal distribution would appear to be an acceptable alternative. So that's what I wanted to show you in this lecture video. I'll see you in the next video.